Alright, welcome back. So today we are going to be looking at something called calorimetry. So this is just more or less a theoretical concept on how we can actually calculate molar enthalpy and enthalpy change for actual chemical reactions and not relying on just looking at a change in enthalpy value. So calorimetry is just a laboratory procedure, that is it, that's used to measure the heat released or absorbed during a chemical reaction. So we do need to make sure everything is in an isolated system for this. Now obviously we're going to look at some of the calorimeters that we use and they're not really isolated, right? So the apparatus, and I just said it, that we're going to use is something called a calorimeter. And it's down below. It's just an apparatus that measures heat flow. That is it. Now remember, and I mentioned this before in one of our earlier lessons, that the system is the chemical reaction being studied, and the surroundings is going to be in the environment around the chemical reaction, which, remember, a chemical reaction is the system which undergoes a temperature change. So it's basically what the thermometer is touching. That's another way. So if you give it a diagram, whatever the thermometer is touching, that's your surroundings. All right? So our calorimeters, whether they're endothermic or exothermic, will kind of look the same. And this is a general basic calorimeter setup where we need an isolated system so you can get, like, you know, some sort of device that is insulated. In the middle, we got our system undergoing the reaction, and basically everything around our system right here is our surroundings. Now also, because this looks very similar to a diagram we've done before, but the difference is that we are going to have I know that looks terrible, but this is a thermometer. Jammed in our surroundings. And what is going to happen for endothermic reactions? Energy is going to leave the surroundings, go into our system, so temperature is going to decrease. And our exothermic reactions will look basically the exact same, so we're just going to have a very crude drawing of just kind of an insulated box. So this way it's an isolated system. We have our system, our chemical reactions somewhere in the middle, or somewhere inside. We have our surroundings obviously surrounding it. And of course we have our temperature, or our thermometer, something to gauge this. Same thing. And of course for an exothermic reaction, it's opposite, so our system releases energy to the surroundings. So we should see the temperature increase in this case right here. So that is going to be our basic calorimeter setups. Now the actual devices that we are going to use in class and that you guys are going to see diagrams for on questions look like this. So our first one is our aluminum can calorimeter, or a tin can, or a copper can, or a metal can. So basically what we have is that we have this setup, so we have our ring stand right here, and the ring stand we have our aluminum can or whatever can attached to it. Inside we normally have water or some sort of fluid that we know its specific heat capacity, and the thermometer is on the inside, and generally we have a burner, or in this case right here it's containing ethanol, burner, or our reaction happening down below. So these are only used for exothermic reactions where we can get a lot of heat generated and going up. These here generally are terrible with regards to getting accurate values. Now the other one you're going to see is a coffee cup calorimeter, and it gets the name because we use a polystyrene coffee cup or a styrofoam cup. Now how these are set up, we normally have our styrofoam cup, or sometimes there's 2 or 3 of them just so they're more insulated. We have a cover to make sure it is isolated. We have our thermometer touched inside. We have a solution, our reaction mixture is what we call, and sometimes a little stir, right, just to mix everything up. These here are generally really accurate and excellent. They're excellent for studying acid-base neutralizations or dissolving things that generally generate heat, or even absorb heat. So like you dissolve ammonium nitrate, it gets colder. You dissolve sodium hydroxide, it gets hotter. And these are the calorimeters that you would use for that. So you'll see both inside questions and everything like that. Now there's going to be 3 assumptions that we need for calorimetry. And one of them is that it's going to be hard, but you just kind of have to make the assumptions that no heat is transferred between the calorimeter and the environment. So it is a true isolated system. Now obviously for that aluminum can calorimeter, when you look back, it's like, you know, aluminum cans, like, it's not an isolated system. If you put an aluminum can of cold anything, or if it's warm, right, or club soda, Pepsi, Coke, whatever, you put it in the fridge, it gets colder because energy is going to go into it. It's not a true isolated system, but anyway, that's one flaw of that one. Another assumption is that any heat absorbed or released by the calorimeter materials is negligible. So we're not going to assume the calorimeter absorbs energy unless otherwise stated. We'll get to one of those questions later. And finally, dilute aqueous solutions, actually almost all of them we're going to see, are assumed to have the same properties as water, and that just means it has specific heat capacity. Once again, unless otherwise stated. So, because we are looking at calculating enthalpy changes due to calorimetry, we know that enthalpy change is the total kinetic and potential energy within a chemical system. So, if we want to get the enthalpy change, we need to look at the difference between reactants and products. Now, using our second and first laws of thermodynamics, we know that the total energy change of a chemical system is going to equal the total energy change of the calorimeter and surroundings, or just the surroundings. So that means that energy lost by 1 is going to equal the energy gained, or our formula, delta H is equal to negative Q. And that negative there just means that, so if our enthalpy change is positive, Q is negative because what energy lost equals energy gained, or if this is negative, that'll be positive. It's just so we keep our kind of signs in order. Now, we also need to make sure that if temperature of the water increases, so we know that energy is leaving our reaction going into our surroundings, well, that is an exothermic reaction. And we have to make sure everything's recorded as negative. And of course, if the temperature of water decreases, meaning that energy is leaving the water and going into our system, then that is endothermic. Alright, so let's look at our first calorimetry example, so using our formula there. It says here, in a simple calorimetry experiment involving burning candle and a can of water, the temperature of 100 milliliters of water increases from 16.4 to 25.2 degrees Celsius when the candle is burned for several minutes. What is the enthalpy change? So one thing that I always like to do for these types of reactions is first identify system and surroundings. So in this case right here, system is always my reaction. So that means my system is the candle. My surroundings is what had a temperature change. In this case right here, it says water increases from 16.4 to 25.2. That is my water. Now the reason I want to do that is you can write down all your information over here on the side, but when we get into more examples, there's going to be a lot of information there. So I just kind of like to go delta H is equal to negative Q. And I also still like to highlight system, surroundings. Now, for this one here, because we have a temperature change, and we know from one of our old equations, Q is equal to mc delta T, we can actually substitute this in down here. So we know delta H is equal to, now this is negative mc delta T. And specifically, mass of water, specific heat capacity of water, temperature change of water. So we got delta H is equal to negative 100 milliliters. Then we use 4.19 joules per milliliter degrees Celsius. And our temperature change final, 25.2 degrees Celsius minus our initial 16.4 degrees Celsius, and we end up getting, I'm just going to write this up here because I just kind of ran out of space. Delta H is equal to, we get a negative 3687.2 joules. And to rewrite this with significant digits, negative 3.69 kilojoules. And that is the correct answer right here. So, same thing with the other one. I want you to read this one as well and give it a try. So what we have here is when 50 milliliters of 1.0 moles per liter of hydrochloric acid is neutralized completely by 75 milliliters of a 1.0 moles per liter solution of sodium hydroxide in a polystyrene cup calorimeter, that's a lot to say, the temperature of the solution changes from 20.2 to 25.6. Determine the enthalpy change. Now, obviously, when we start writing our stuff down, right, there's just a few little things. We have our system, and this is the neutralization reaction in our surroundings is our solution. Now, you will notice that it doesn't say anything about what this, it's just a solution. So this is when we're going to have to take one of our key points on back here, and that if we have a weak, dilute, aqueous solution, it has the same properties of water, specifically 4.19 joules per gram degree Celsius. So we need to make sure that we assume that this solution is in fact water. Now there's one more trick that you also need to highlight as well, and that is if you notice we have start with 50 milliliters of one solution and we add 75 milliliters of another solution. So our total volume are the combination of those two solutions. And that is our 50 milliliters plus our 75 milliliters. So when we are done, we should have a combination of 125 milliliters in total. All right, and that of course matters. So obviously I don't have enough space to finish here, but I will complete that one over here. So in the same vein as last time, we start with delta H is equal to negative Q. And we know this is my system referring to my reaction, and this is from my surroundings. Just like before, we're solving for delta H. So it's negative MC delta T. Now this time, because the total volume of the solution was 125 milliliters, that is my total M. C, 4.19 joules per milliliter degrees Celsius, and my change in temperature is of course 25.6 minus 20.2. And when we do this, we get delta H is equal to negative 8.25 joules. And to get this down to a more reasonable number, I divide by 1,000 to get my answer in kilojoules. And with correct number significant digits, I get 2.8 kilojoules. Now, if you just want to represent your answer as in scientific notation, it works as well, because I don't specify it must be in kilojoules. So if you're ever given a question where you do have two solutions coming together, you need to make sure you add up the volumes of both solutions. Only if we're adding two solutions together, though. Now, we will notice that I was kind of just, for a lot of these questions, it was just, what is the change in enthalpy? Now, for the most part, we're going to get ones where we need to find the molar enthalpy. So this was the original equation I was giving you. If we expand our two equations, so we know delta H is equal to NH, so that's that part, and then Q is equal to MC delta T. So we have our equation, where we have NH system is equal to negative MC delta T. And of course, we have all of our values right here, right? So remember, N moles of the reactant, H molar enthalpy of the reactant. So this side right here, our NH is for our system or our reactants, whereas our MC delta T, mass of surroundings, specific heat capacity of the surroundings, temperature change of the surroundings. So let's look at solving some questions. So right away you notice it's different, where it says when 5.23 grams of solid sodium hydroxide is dissolved in 1 liter of water, the temperature of water goes from 18.0 to 31.9. Calculate the molar enthalpy of NaOH. So what we have is the same thing. We want to make sure we specify what is system and what is surroundings. What is our reaction? In this case right here, it's dissolving, but still, it's still a process. So we have our system. It's NaOH, right? Because it's dissolving. Our surroundings, I'm just going to write surround, is of course our 1 liter of water, because that temperature change. Now, when we look at our equation, NH is equal to MC delta T, negative. Now we have to remember, this side, NH is for our system, sodium hydroxide. MC delta T is for water. That means do not put 5.23 in here with that M. Because remember, this side right here is for water. This side over here is for sodium hydroxide. So that means we do need to use this mass of sodium hydroxide, but that is to find N. Alright, now you can do this equation really quick off on the side. If you want, number of moles is equal to mass over molar mass. Right, and that's where we take our 5.23 grams divided by molar mass for sodium hydroxide is 40.00 grams per mole, and we are left with 0.1308 moles. So, if you want to just rearrange and solve right away, you can. Or you can put in the numbers here. I like to rearrange and solve in the one shot, because we know we're solving for molar enthalpy. Negative MC delta T over N. And I can put in all my values. So I know negative, the mass of water is 1.00 liters. Specific heat capacity is 4.19 kilojoules per liter degrees Celsius. And the change in temperature is 31.9 degrees Celsius minus 18.0 degrees Celsius. All of this is over the number of moles of sodium hydroxide, which is 0.13075 moles. I know I had 108 there, but I had to round that early just to kind of fit it in. This is with a few more decimal points. And when we are done, I'm just going to write the answer up here. H is equal to negative 445 kilojoules per mole. And that is my answer. Alright, so that is where you definitely be careful as much as you can about what are the units and what's everything there. So that's why I like to go over on the side here, right at my system, right at my surroundings, and know also that this side is for systems, and H is always for my system, MC delta T is always for my surrounding. So I make sure that all the information for water stays on one side, all the information of my system stays on the other. Now, obviously for the next few, if you want to, pause the video and jump right ahead into this right here. If not, I'll do the exact same thing with this one, how we solve it and all that. So what we have is a 200 gram cold pack made of ammonium nitrate is placed in 200 milliliters of water in a coffee cup calorimeter. The water had an original temperature of 20 degrees Celsius. After the reaction, or in this case it's a dissociation, not so much reaction, the final temperature is 2 degrees Celsius. What is the molar enthalpy of the cold pack? So, same thing. We have our system. In this case, it's our ammonium nitrate, because that is the thing dissolving. And ammonium nitrate is NH4NO3. Our surroundings, in this case right here, is our water. Okay? So same thing as before, NH is equal to negative MC delta T. Remember, NH is for system. Negative MC delta T is for our surroundings. Now we have 200 grams of our cold pack. Now remember, cold pack of ammonium nitrate is our system, so therefore I need that 200 grams to solve for number of moles, which I'm going to do off on the side right here. So number of moles is equal to mass over molar mass. We have our 200 grams divided by the molar mass of ammonium nitrate, right? I have right here, so NH4NO3 is 80.06 grams per mole. And we got N is equal to 2.4981,264 moles. So we're going to use that number for N. So same thing, I'm going to rearrange the equation. H is equal to negative mc delta T all over N. When I fill in my numbers, H is equal to negative, mass of my water was 200 milliliters. Now, you can write this down and have your answer in joules. I know for the most part, molar enthalpy is always in kilojoules per mole. So I'm going to convert this into 0.200 liters. So my specific heat capacity can be 4.19 kilojoules per liter degrees Celsius. So I can get my kilojoules that way. Now, when you're writing down temperature, just be careful. Because here our initial temperature is 20, our final is 2. So our delta T, we go 2.0 degrees Celsius minus 20.0 degrees Celsius. And we put all this over 2.4981,264 moles. And we get our answer this time. H is equal to a positive 6.0 kilojoules per mole. That is that one. Now, of course, we do know because the temperature was going down, it's endothermic, and it should be positive, and that's what it is. Now, for example 3, so we've done the 2 examples right there. Just try this one on your own. Pause the video and give it a go. We should get in this one right here, H should equal negative 1,262 kilojoules per mole, which you convert this into scientific notation, or, I've done this as well, you can write negative 1.26. If we want to use a different prefix, we can use megajoules per mole. That'll be the same thing as well. All right, so give this one a try. In this case right here, we have ethanol. If you're wondering about what is the chemical formula for ethanol, some of the ones in your data booklet, like here, if you look up ethanol or look in your E's, you can find the chemical formula. It's right here, C2H5OH. Do not use this value though. This is formation reactions different. So C2H5OH, ethanol. If you want to get that one done. All right, I just want to bring light to example 4. Same thing. This one here is just a little different. This one here, calculating molar enthalpy of neutralization of HBr and KOH. Now, just be careful, like we've had a neutralization reaction before where we added a solution and a solution. This one right here, this is the only volume given, so this is the only volume of solution. But what you should get, A, you're going to get the molar enthalpy of HBr to equal negative 28.5 kilojoules per mole. And for B, you should get the molar enthalpy of KOH to be negative 32.0 kilojoules per mole. Once again, pause this and give it a try. If you don't get this, you can hop on Google Classroom, look up the answer key for the notes right here, and I'll have the answer key there, so all the workings for it. All right? But I want you to challenge yourself and see if you can get those as you're watching this. Now, the last one I just want to bring you to, this one is a special type of question where it says a student built a simple calorimeter with a 25.0 gram tin can and 150 milliliters of water. All right, so we have a tin can and water. But if we keep reading, so we do calculate the molar enthalpy combustion of ethanol, so we know our system is ethanol. Our surroundings, though, if we keep reading, it says Find the molar enthalpy of combustion for ethanol if 0.166 grams of this fuel increase the temperature of the calorimeter and its contents. So now our surroundings are actually two things. We have our calorimeter, so we have our tin can and water. So because it's specifically saying that both things underwent a temperature change, so we're going to have to calculate both of them. Now, funny thing is, I'm just going to get you set up and hopefully you guys will be able to finish this on your own. So, and I also have this right here, so remember including the heat gained by the water. Another thing we can imagine is that all we've been doing so far was only one thing was changing temperature, and we've had our delta H is equal to negative Q. Well, technically, we can write Q total, because if we have multiple things gaining energy, well, we can find the Q value for multiple things. All we need to do is just add them together. So in this example, we're going to get delta H is equal to negative, in this case right here, it needs to be the Q of our tin can, and we're going to add it to the Q of our water. So how this is going to look later, I'm going to expand some more. So NH is equal to negative. Now remember, Q of tin is going to be MC delta T, all for tin, plus MC delta T, all for water. Okay? Now remember, make sure to specify this MC delta T is for tin. This MC delta T is for water. And when we look at it, the mass of tin is here, right? So mass of tin, specific heat capacity of tin found in your data booklet. Change in temperature, 7 degrees Celsius. Mass of water, right here, 150 milliliters. Specific heat capacity of water, you can find it. Same thing, delta T, given right here, are 7. So that's just setting that one up. So I want you guys definitely try this one on your own, putting in the numbers. Now, same thing as before, you should get H is equal to negative 123.229 kilojoules per mole, or negative 1.23 megajoules per mole. So I want you guys to try this one, see if you can get the answer. If not, same thing. Look at the answer key in Google Classroom. That one's up there, and you can see all the numbers step by step on how I got this one. All right, but that is once again a very special case when the calorimeter is brought in. We know the identity of the calorimeter, and of course we know the temperature change of the calorimeter. You will do a lab based on this one as well, where we are going to find the combustion of both methanol and ethanol, and how we solve this lab and the performance test that goes along with it will be the exact same thing as this. So make sure you try this one and give it a go. And of course, same thing, there are 2 diploma exam questions that you want to try. So once again, read them, figure out what the answers are, check the answer keys on Google Classroom there as well. And same thing as before, if you have any trouble whatsoever, make sure to let me know so we can sit down and hopefully go through these here, whether it's something like this or a Google Meet, or we can meet in person if you're not isolating and stuff like that. All right, so that's the case. That's it for this one. See you guys for the next one, where we're looking at Hess's Law. All right, see ya.